Hi, welcome to my channel, Jabber Time. Today we're going to cover the fundamental theorem of calculus, part 1 and part 2. As you can see, there is main formulas listed here on the first slide. And I'm going to go over 16 examples. The first 12 or so will be kind of quick, but I'll slow down towards the end. The reason why I have enough examples is I want to show you or expose you to enough ideas about integration. Because after Riemann sum, all what we do is integration. And one example is not going to be enough, two is not going to be enough. I need also to get the fundamental theorem of calculus involved in my examples. Let's get started. The fundamental theorem of calculus. Area functions. If you see in this graph, we have a function that is continuous and differentiable. Y equals f of x, and we are going from a, which is a constant, that's my start point, up to x, which is a variable. So x could be here, could be here, could be here. As we move away from a, the area is gonna increase. So what we have is area as a function. T is my dummy variable. X is my main variable. This is a new concept. And as you could see, that's the reason why I'm slowing down, because you need to understand what's happening right here. As we go on, if we stop at B, we're done. We're just like boxing this and we are doing it, which is Riemann sum. But if x is a variable, we're dealing with functions of a new type, not the curve, the area as we go. So the area as a function of x will have a start fixed point A and an end point that is moving, which is called x. I can't write here f of x dx, it's f of t dt. X is being called the independent variable of the area function. That's my independent, that's a major part. And t will be called the dummy variable, the variable of integration, dt, and it's a dummy variable. You could call it dz, you could call it anything you want, but the independent variable is what is up here, which is x. Here's part 1. The fundamental theorem of calculus comes into two parts, part 1 and part 2, just like in movies, part 1 and part 2. So here's part 1. Sometimes part 2 is more interesting than part 1, and sometimes it's not. Let's take a look and we'll see which one do you like more. If f is continuous from a to b, the area function that I just mentioned, and I gave you the graph, will be as follows. Is continuous on AB and differentiable on AB. A prime of x is f of x. The derivative of the area function will take you back to the graph, which is f of x. Those are formulas that it's hard to grasp, understand quick. That's why I'm slowing down, and hopefully by the end of the video you'll understand what I'm talking about with these formulas. A prime of x is the derivative of the area function. This is the area function, d dx applied to it. Instead of calling it a, we're going to call it a prime. That is, the area function of f is an antiderivative of f on the interval a to b. This was part 1. Interesting, right? That's what calculus is. Concepts beyond imagination, calculus with vision. You know, who would think that with calculus or integration, we could find any area under a curve, any type of curve. And we could connect between the function, the graph, and the area under the graph. Okay, Riemann sum is a great concept. The tangent, which is the derivative part, was a great concept too. Here's part 2. F is continuous from A to B. Capital F is an antiderivative of F on A to B. The way I think about this right here, small f and capital F, to help you understand more, when you find derivatives of, let's say, functions like x to the power 5, the derivative of 5x to the power 4, it gets reduced by 1 degree. So integrating 5x to the power 4 will take you back. All right, of course, plus c if you don't have a and b involved. So one function is lower by 1 degree, the other function is higher by 1 degree. Think about the higher degree is capital F and the smaller degree is small f. That's one way to connect between both. So when you find derivative, you're going to the lower degree. When you integrate, you go back to capital F. All right. Integrating the small f will take you back to the capital F. Since I have limits a and b, we're going to plug in b in our result function, integrating, and we're going to plug in a and subtract as follows. That's part 2. There is more into it, but here's more detail about this right here. Integrating from a to b, that's the limits of integration of f of x, which is called integrand. Dx with respect to x, x is the variable of integration, will give you capital F of x from a to b. This is a shorthand notation, and that's how we do it in steps. We plug in b, we plug in a, and we subtract as stated. There's a very interesting part of this section. It's called the inverse relationship between differentiation and integration, which is kind of like what I'm talking about and mentioned earlier. Capital F, small f, and so on. The derivative of the integration will take you back to the old function or the original function. Do you see the relation between differentiation and integration? Differentiation gives you the slope of the tangent. Integration gives you the area under the curve, but both are related by the idea of the derivative of the derivative of the integral takes you back to the function. So you have a graph, you have a function, find its derivative. You're going to go backwards, find the integration of the derivative. That's what I'm trying to say. So the derivatives, the integrations are kind of like two parts, but they are related with steps in math by integrating the derivative will take you back. And finding the derivative of the bigger function will take you back to the lower one, if you want to say it that way. From a to b, f prime of x dx will take you back to f, that's f prime, that's f. The integration of the derivative will take you back to the original function f. Pretty much you see that there is a lot of ideas or concepts, and that's why I have enough examples in this section. The first examples, probably I think there are first 12, if I remember. I'm going to go a little bit fast. Just want to expose you to it. There will be timestamps for each one of them. So if you want to visit or go back to each any one of them, you just click on the timestamp and it will take you there. The more examples that you could see, the more that you're going to benefit from this section. Some other sections kind of feel like, you know, they stand alone, kind of quick. You see them once and you're done. You don't feel like you want to see it like 5 times. So here we go. Here's the first example, and we'll see how it's gonna go if I go fast. Hopefully you understand what I'm talking about. So we're going from 0 to 2, 4x cubed dx as an integration. What we do is we increase the exponent by 1. We divide by the new exponent. That's gonna be 4. We divide by 4, which is gonna cancel. And we end up with x to the power 4, clean, from 0 to 2. Notice without plugging in 0 and 2 and so on, take this right here. Find the derivative of it. The 4 goes down and this gets reduced by 1. So it's 4x to the third. It's right there. Integration of a function takes you back to the original. This original, find its derivative. You get what's inside. Now we are finding the area within exact limits from 0 to 2. So we plug in 2 first, and then we plug in 0, we subtract. This is the fundamental value theorem part 2. Do the math, and you get 16. One more time, if you feel like I'm going too fast, you could go back and visit. This is example number 1. Example number 2. Still polynomial, straightforward. 3x to the second, 2 is going to increase by 1. You divide by the new exponent, 2x to the power 1. It's not written, we agree on it. Add 1 to 1, which is 2, divide by 2, and then plug in 0 and 2. As you could see, I did not write over 3 and cancel the 3 because it becomes so simple to us, straightforward. Alright? That's why I want to show you more examples. You could see it and you could just see the flow, and I'm building as I go, as you could see. Plug in 2 first in the whole package, then plug in 0 and subtract. That's capital F of B minus capital F of A. Since we have definite integral, so we have A and B, we're not writing plus C. Answer is 12. And third example. This time we have a fraction as an exponent. I know some students, they don't like fractions and don't like negatives. Alright? I joke around a lot in classrooms, and because this is a YouTube video, I try not to. I don't know if this is right or wrong. Let me know if you feel like I should add more comments and more jokes. I do a lot of jokes in my classrooms in person. Okay, that's how I teach. That's my style. I tell my students, do you like fractions? They go like, no. I go like, I know. Do you like negatives? They go like, no. I go like, I know. Usually Americans don't like negatives and don't like fractions. And I'm American too, but I don't know what to say. They don't like negatives and they don't like to be natives or native. Alright? This is part of the game. They like to see 1 and 5 and 7, but they don't like to see 1/3. That's it's not a joke, but something that I get their attention to in classroom, and I start talking back and forth instead of them just watching me and they get sleepy. So we're gonna add 1 to 1/3, and we're gonna divide by the new exponent. That's 4/3. Dividing by a fraction like this, that's called mixed fractions in math. We're gonna take this division, change it to multiplication, and instead of multiplying by 4/3, I'm gonna flip it and call it 3/4. Between 4 and 8, it simplifies. Do the math. And 1 and 2, 2 times 3 is 6. Plug in 8, plug in 1. Now, how do you plug in 8 if you don't have a calculator? No problem. We'll take the 4/3 as 2 parts. The 1/3 first, which is a cubic root. Then we'll apply the 4th. This is 4th. This is 1/3. That's not our 3. It's called 1/3. Cubic root of 8, when you plug in 8, you get 2. Now you apply 4. 2 times 2 times 2 times 2 is 16. Sorry if I'm going too fast, guys, but I think you could follow me. This is calculus. That's not a lower math. I just want to expose you to more examples so this integration concept becomes natural and simple to you. All right? And so you could help your friends when they ask you questions about integration or anything of calculus style. Final answer 90, and that should do it. One more example. Enough of x's and regular ones and fractions. I think we need to see different ones. Here is a cosine. Where do you think the answer is? In other words, my question to you, what's the function that you go back and find its derivative, it gives you cosine? You might say, well, the 2 is in my way. Not really. 2, you could put it up front. Earlier we had the, what did we have? We had the 8. Did you do anything? No. It's almost like it's outside of integration. I just had to simplify later on, right? So the 2 does not affect my thinking about what's going on. I need a function that its derivative cosine and its integration will take me there. That's a sine function. So we plug in pi over 4. We want to make it easy on you. It would be nice to practice pi over 4, pi over 3, pi over 6, not pi over 7, unless if you're going to use a calculator for that, but who cares? In classrooms, we want you to practice. It's not like the idea we want to give you a hard time. We just want to give you practice. Pi over 4 is convenient, so you could do it and move on. We plug in pi over 4, plug in 0, subtract, make sure that 2 is for the whole thing. You could keep it with the sign as you go, or you take it out as a common factor from f of b minus f of a, if you want to call this one capital F of x. All right? What's sine pi over 4? And what's sine 0? You need to know those basics, how sine looks like. Sine goes up and down, then back up. Sine pi over 4 is right there between 0 and 180 degrees. So it's, between 0 and 90 degree, which is 45 degree, and it's right 2 over 2. Sine 0 is just 0 because it starts at the origin. Numbers simplify nicely, and that's how we should start. We should start with examples that go smooth and quick to understand the concept. Square root of 2 is the answer, and we're done. Let's take a different one. Fractions. We're back to fractions. We can't get away from fractions. How do you handle this? Well, we know that integration of x to the power n is x to the power m plus 1 over m plus 1. So how can I see this as a power? Not bad. Take the 2 out. Take this, read it as x to the power half, because that's the meaning of square root. Bring it to the top, so no more fractions, and make it negative exponent. Negative half, add 1 to it, and divide by the new exponent. When you add 1 to it, becomes half. You divide by half, but why would you divide by half if you could reduce your steps and multiply by 2 over 1? That's called 2 steps in 1. Actually, it's called 2 birds, 1 stone. Alright? 2 birds, 1 stone. 4 from here, that's a square root. Gave you some nice numbers, 9 and 1. Even though my 9 doesn't look right, but that's my handwriting, and I'll do my best to make it clear on my slides. Square root of 9 is 3, square root of 1 is 1, 3 minus 1 is 2, 2 times 4 is 8, and that should do it. We're done. One more example. We're gonna take now a fraction, but more into it. How do you handle this? That's called distributive property. I know that students, when they think about distributive, they think about multiplying, but it comes also in 2 forms, because multiplication and division are pretty much 2 faces of the same coin. Instead of dividing by 2, you could say I'm multiplying by half. Same thing. They go together, all right? So how is that distributive? Oh, I see. we're gonna divide this whole thing by this much. So I'm gonna divide this by this and this by this. That's called distributive. Make sense? All right. And this is not a fraction anymore. That's an easy number. And this one, we had it before. You see why I gave you more examples? I just want to build up and show you more and more and more. So, first part is handy. Second one is just 1. Add 1 to this, divide by half, which is flip it, and it'll give you 2. And you have another 2, that's a 4. And plug in 9, plug in 4, subtract, and you get the story. As you could see, I'm repeating myself, and the answer is 9. 9 is a good looking number, and we're done. Let's take something different, completely different. Integration of e to the x from 0 to ln 8 with respect to x. What's the function that you find its derivative and it gives you e to the x? Which is a very interesting function in life, and it's the only function in life that behaves its own way. No other functions in life behaves like e to the x. Its derivative it's itself, and the integration also it's itself. So it's e to the x from 0 to ln 8. Plug in ln 8 for x and plug in 0. E to the 0 is 1. Anything raised to the 0 is 1. E is the inverse of the natural log, so they cancel, and it will drop down by itself because you can't leave it up. Just kidding. So it's 8 minus 1, and the answer is 7. 7 is even much better number than 9 earlier. I think if you choose between 7 and 9, you're gonna pick 7. Alright? Alright. Different example. 1 minus x times x minus 4. Why do I have this example? Because I want to tell you something. In differentiation, we have a rule that's called product rule. Do you remember? F times g prime will be f prime times g plus f times g prime. Alright? We don't have that in integration. We don't have a product rule for integration. We just don't. Alright? So you have to find some other way, because this is simple. I would say the best way is distributive, multiply them together and have them as a polynomial. Then I think the story after that is just like regular math for us now. You increase the exponent, divide, increase the exponent, divide, increase the exponent. Oh, you don't see it here? It's x to the power 0. If you want to see it as an exponent, add 1 to 0, then divide by 1, and plug in 4 in the whole thing, plug in 1 in the whole thing. I even skipped that. You could see that. It's just like, you don't have to see it on the slide, and it's going to be a waste of time. We know it, we believe in it. It's 9 over 2, and it's a fraction, but that's fine. You could leave it. We could handle fractions this way. Let's take a completely different one. Well, how do you handle this? Well, at this moment, I don't think you have enough experience to handle it. Sometimes you have options to look in the back of the book. In the back of the textbook of every calculus, there is a list of formulas for differentiation and a list of formulas for integration. If you notice, just take a look when you have a chance. Integration is a lot more rules than differentiation. We're missing the product rule, we're missing the quotient rule, and it's harder to integrate sometimes than differentiate. For this one here, you might not know where it's coming from, but let me just make the story short and tell you where it's coming from. It's coming from sine inverse x. The derivative of sine inverse x is what you see, 1 over square root of 1 minus x squared. Okay, plug in 0 and half. Well, we gave you numbers that you could handle with sine inverse. I think everybody knows what's sine inverse half, or in other words, what's the angle. If you apply sine to it, it gives you half. That's 30 degree in degree mode. For the convenience, we say degrees sometimes, or pi over 6. Sine inverse 0 is 0 because 0 takes you to 0, applying sine because sine starts from the origin. That's the answer, pi over 6. Let's take another trig one. Secant inverse comes from, if you remember, comes from tan. The derivative of tan is secant inverse, so the integral of secant inverse is tan. We gave you some nice numbers to deal with. And do you remember tan pi over 4? Tan 45? Isosceles right triangle, opposite over adjacent. Well, it's isosceles. It's the opposite and adjacent are identical, so it's going to be 1. 1 minus 0 is 1. Let's take another fraction. 3 over x. This time we're not gonna take x to the top and make it -1, because if you do that, -1 plus 1 is 0. And then you're gonna go like, oh, I have x to the power 0 over 0. No, that's not what we want. We know that the derivative of ln x is 1 over x, but to be on the safe side, usually we write ln absolute value of x, even though I don't need it here, but I wrote it down because I want to remind you that sometimes you have to be careful. Ln, if you graph it, it goes on the x and y axis this way from the 4th quadrant to the 1st quadrant. In other words, the domain of ln x is positive numbers only. If you try on a calculator, ln -5, for example, it's not gonna give it to you. It depends on the type of the calculator. It's gonna display a message to you that out of domain or error, try again, or call a friend. Alright, so we're gonna plug into, see, I took the absolute value, I don't need them. Ln 2 minus ln 1. What's ln 1? Well, the graph one more time goes this way. You go this way and it passes through 1 on the x-axis. So that's a 0. One of the order pairs on the graph is 1, 0. The x-intercept of ln x is at x equals 1. Alright, we're almost done. 3 ln 2. How could you enhance this even more? Let's say it's a multiple choice. And this is not one of the 4 choices. But looks like somehow I'm getting close, but I don't see it. Well, maybe they went further than that by taking the 3 back n on top of the 2. This is what I mean, which is ln 8. So if it's a multiple choice and they gave you ln 8 and give you some different ones, that's the answer, ln 8, because you did not complete, and there's steps that you could even go further and simplify it even more. 3 ln 2, I know it's equivalent to ln 8, but for multiple choice, it's good to know enough about ways of simplifying things till the end. All right, let's take now something more interesting. All these examples, I believe they are 12. They're just practice. Knowing integration, how do you integrate fractions, polynomials, trig functions, plug in B, plug in A, and subtract. Here's more interesting questions. The derivative of a function, area function from 3 to x. Notice I wrote 3 in blue, and I'm highlighting the x's for you because t is a dummy variable and we don't care much about if it's t or u or c, it doesn't matter. This problem is not me, I'm writing the answer, it's just like one step. There is nothing in it. Here's the answer. It's x to the second plus x plus 1. Compare this to this and you'll see where I got it from. Let me say why. Derivative of an integral function, they are inverse of each other, they cancel. And we are dealing with x as my main variable, so that's my original function. That's it. I'll take you back to the first slides when I mentioned the inverse relationship between differentiation and integration. The derivative of the area function is the original function. The original function is not f of t, it's f of x. Let's take one more. What do you think the answer is? I wrote here 1. Earlier I wrote 3. It doesn't make any difference. So if you go back, what do you see here? It says a. This a could be anything as long as it's a constant. Keep that in mind. So what do you think the answer is? Sine square x. And you know the reason why. Alright? Fundamental value theorem part 1. Let's take now a higher level one, and we'll close this video with this higher level one. I think this is the last one. Now I need to find the derivative of this area function, but look at this. It's not x. It's x to the second. And look at this, it's not even cosine t, it's even cosine t to the second. So how do we handle? I'll slow down so I could make sure that you understand my steps. The upper limit of the integral is not x, but it's a function of x. Thus, the function to be differentiated is a composite function, which requires the chain rule. See this right here, for example, it's not cosine t. If this is a function, call it g, and this is f, this is f of g. That's what they call it, composite function, and that's why we need to go further and apply the chain rule. We use the chain rule concept in differentiation, we have it in integration. This is detailed. After this example, I remember I'm gonna go over one so quick. All right, just be patient with me with the notes, because we can't just like jump to the quick steps without slowing down and seeing the concept. Let u be a equals x to the second. That's right here. So focusing right here, what's du dx? 2 is gonna go front, 2x. Now our y, it's this guy here, is a function of u. Instead of x to the second, we're replacing x to the second with a letter u. We're going from 0 to u, cosine t dt. Alright? By the chain rule, d dx of 0 to the x to the second cosine t to the second dt equals dy dx. This is my y, and here I should have t squared. I just noticed that it's a typo. All right, now dy dx, this is y and this is d dx. Dy dx could be written as dy dx and du in between. So it's dy du times du dx. It's kind of like du cancels to agree with this. What's dy du? It's a ddu of y. ddu of y. This is y. That should have a t square right here. And what's du dx? It's 2x. Alright? Cosine u square. This is ddu of integration. We'll cancel each other and we'll write u right here, and that will do it. From the previous problem, we didn't have a square, but same concept. The integration and the differentiation with the same variable, they cancel each other, and this is my main variable. T is a dummy variable, so I'm gonna end up with cosine u square. and we agreed on this, and this is what we have. We still have to clean it up. We'll put 2x up front, and instead of u, we take it back to x to the second, and we have another second or exponent of 2 here, makes it x to the 4, and that's the answer. Okay, let me go over this so quick so you could help me understand the next one or follow me with the next one quick without that much writing. Take a look. We need this. Let's look at this and look at this. All right, skipping all what's in between. We are doing opposite operations, integration and differentiation. We take this, put it right here, but because it's a composite, we need to go on as a chain rule. Put this right here, x to the second, right there. What do you see? Cosine x to the second. Okay, what is chain rule? You go after x to the second and find its derivative, which is 2x. Cosine x to the second, which is cosine x to the 4 times 2x, right there. That's it. Okay, I don't want to keep repeating myself. Let's look at the next example. Let's think. What do you think? That's not x, so chain rule is involved. We're gonna plug this in right here. We're gonna continue after this, go after it and find the derivative of this. Here we go. Plug it in, go after this with a derivative, simplify, and you're done. That's the answer. All right. I thought that this was a last example, but I felt maybe so excited. I want to show you more and more and more. And here's another one. Oh, this one did not start from 0. Let's see the last one. Yeah, start from 0. They want to make it harder for me. No problem. Let me show you the steps. We're gonna go from e to the x, stop at 0. Then from 0, continue. But the formula does not say start with x or u and go to 0. It says the other way around, start at 0. So how can I flip this and start at 0? We use properties of integral. We flip it and we insert the negative sign. Fair enough, right? Okay. We're gonna take this, plug it in right here. We're gonna take this, plug it in right here. We're gonna go after this as a chain rule. What's the derivative of e to the x? Still e to the x. What's the derivative of e to the 2x? E to the 2x, another chain rule applied, times 2. Do you guys see everything? After this, we're going to just simplify. Now, this 2 goes up front, as you could see. Ln and e are inverse of each other, they cancel. Here, 2 goes up front. Ln e to the x, still in black. Ln and e, they cancel. This x does not stay up there, it will drop down. And this 2x won't stay up there, will drop down. And that's my final answer. And hopefully I did my part, helping you or exposing you to enough examples and concepts about the fundamental value theorem. The only thing that I feel like I did not cover is when you have a step function or two graphs, let's say you go straight, then you go on a curve. To integrate, you need to go under the straight one, finish, then go under the curve one, finish, and add them up. So you're gonna go like from A to B, wherever that be, between the line and the curve, and from B to whatever they want you to go to C, and partition the integration into two parts from A to B, then from B to C, because each part is under a different graph. I did not cover that, and it's kind of hard to cover every single aspect on videos, as you could see, but I'm doing my best. And this will keep going, as you notice. In a week or two, I'm gonna start building college algebra videos. I'm gonna add algebra, and I'm gonna add some stats, and I'm gonna add calculus 3, vector calculus 3 dimensions. Last semester, end of the semester, when this whole story began, I started my calculus 4 videos. If you notice on my channel, I do have differential equations. So I'm hoping, I'm planning within a year or so, I'm gonna have enough of calculus 1 and 3 and 4 and college algebra and some other math, because I teach math 104, math 106 at college, regular semesters. That's for math reasoning for elementary teachers with activities and more. I'm gonna build also videos for that. So if you like my videos, I would really appreciate it if you hit the like button, if you subscribe also, that would be great. The more that I see more likes, more people subscribing, it kind of like pushes me to do more. Imagine if you make like 100 videos and you see that nobody's watching them. Would you keep going? I don't think so. You would record them for yourself, but when you put the lights and you try to make a microphone and do the right settings, I think you're doing it for the audience, and you are my audience, and I really appreciate if you could support me and let me keep going. Hopefully enough math will be up soon, and I'll be also improving in more aspects like lights, microphone. I'm shopping around for microphones. I do have one, but I need a good one, let's say, that makes it more enhanced. All right, there is even more. So thank you for watching, thank you for listening to me, and hope to see you again. Share it with friends. I'm sure if students want to take calculus next summer or some other classes, let's say they're waiting for fall semester, spring semester, and if they need some help with calculus before even they take their calculus class, they could watch my videos and they could just go into that class. It doesn't have to be me, some other teachers, and they will have enough knowledge about what is calculus, what's limits, limits at infinity, and derivatives, formulas, fundamental value theorem, and more. Thank you for watching, and thank you for listening, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.